Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 16, seminar 7, in which we will solve our next problem, number 17, the objective of which is to find a way to invert two coplanar distinct circles that are not in contact into two circles that are concentric. And from the nature of the statement of this problem, it follows that in this case, we have only two cases to consider. In the first case, neither circle contains the other, which means that the mutual juxtaposition of the input circles looks something like this. Two circles, distinct, coplanar, not in contact. And in the second case, one of the input circles contains the other, like so, for example. For demonstration purposes, I will solve this problem as it pertains to the first case, the case of no containment, and I will leave the second case, when one of the input circles contains the other, as an exercise to the viewer. As such, assume that the first input circle, lowercase q1, shown in yellow on your left with the center at the point uppercase q1, is given, and the second distinct coplanar circle q2, shown also in yellow on your right with the center at the point uppercase q2, is given. These circles are not in contact and neither circle contains the other. In this particular mutual juxtaposition of the input circles, it is pretty much guaranteed that the centers of these circles, the point uppercase q1 and the point uppercase q2, will be distinct, and in any plane, two distinct points define a unique straight line that passes through these points, and in the theory of circles, we refer to that straight line as the straight line of centers, or just the line of centers, lowercase l. I designate it over here in blue as the straight line L is a straight line that passes through two distinct points, uppercase q1, uppercase q2, which are the centers of the two input circles. And this is already good news, because by definition, that straight line is orthogonal to the input circles q1 and q2. And what does that mean? That means if we strategically somehow place the center of inversion somewhere on the straight line of centers L, then precisely because that straight line will pass through the center of inversion, that straight line will be taken into itself. And because we already know that according to the appropriate theorem, the magnitude of the angles between two cooperating curves under any inversion is preserved, whereby cooperating curves we refer to the curves for which the angle between them can be sensibly defined. That means that the images of the circles q1 and q2 must be orthogonal to one and the same straight line L, because that straight line L is taken into itself. And that means that the centers of the image circles must be located somewhere on the straight line L. We have, in general, uncountably, infinitely many candidates, and in general, the centers of the image circles will be distinct. But we want to manufacture somehow a situation where these two distinct centers merge into a single point, because it's the center. If the centers of two circles merge into a single point, then what? Then these circles become concentric, and thus we solve the problem, because the requirement here is to reflect the given input circles into two circles that are concentric. The question is, how do we limit, or how do we enforce that merging process of two distinct points into one? Well, in a wishful thinking manner, it would be nice to somehow, again, manufacture a situation when the centers of the image circles of the circles Q1 and Q2 under an appropriate inversion of the parent plane with respect to a circle must also live on a straight line that is orthogonal to the straight line L, because then we will have the ability to use the so-called method of intersecting loci, and that is the first idea that you were expected to generate on your own. If we have a situation when the centers of the image circles must live on one straight line, and at the same time the centers of the circles must live on another straight line that is orthogonal to the first one, then necessarily all four candidates must merge into one, and voila, we will have one point that plays the role of the center of two circles at once, and with us satisfy the requirement of concocting two circles that are concentric. The question is, how do we manufacture that straight line that is orthogonal to L and that houses the centers of the image circles, of the input circles Q1 and Q2? Well, this is the second place where you were expected to generate the second idea of your own and bring the notion of radical axis of two circles. I recorded it over here. Lowercase a is the radical axis of the circles Q1 and Q2. That straight line visually is shown over here on the right side of your screen. It is shown in red. This is a straight line right here. And from the previous lectures, we remember how we construct that radical axis of two circles that are positioned mutually with respect to each other as shown. I did not want to introduce more clutter than I have to, but you remember the Euclidean tools only construction. We construct one common external tangent to both circles, and then we cut that common tangent in half, and through that point perpendicular to the line of centers we snap a line, and boom, voila, that straight line orthogonal to the line of centers that passes through the middle of the common external tangent is the radical axis. And what fact about the radical axis of two circles comes to mind that is useful to us? Well, we remember that any one of pretty much uncountably infinitely many points on the radical axis, barring some small number of exceptions. When the two circles intersect, we cut out the part that is common to two circles, but for the most part, any point on the radical axis, of which there are uncountably infinitely many, can play the role of a unique circle that is orthogonal to both circles Q1 and Q2. And how do we construct such orthogonal circles? Well, through the chosen point, such as the point Q, for example, we snap a tangent to any one of the circles. For example, tangent to the circle Q1, we identify the point of tangency A, and then voila, we have locked in the radius of the unique circle that is tangent to both of these circles. Now, like I said before, the radical axis represents uncountably infinitely many candidates to play the role of the center of the circle that will be orthogonal to both. But out of this uncountably infinitely many, we need to choose one, and we need to choose that one point, one center, wisely. Why is that? Well, let us say that our radical axis of the two given input circles intersects the line of centers at the point Q. That point is shown in red over here. This is the point Q, where the straight line of centers of the input circles and their radical axis intersect. Then, again, using the Euclidean tools alone, it is entirely possible to snap a tangent, let's say this one right here shown to your left, a straight line that is tangent to the input circle Q1 through thus defined point Q. The point of tangency in this case I will refer to as uppercase A, and voila, by definition that means that the line segment or the straight line Q1A will be orthogonal as shown with the squarey looking formation here to the straight line that passes through the points Q and A, and that precisely means that the circle, which we will name Q, that has the point uppercase Q as its center and the line segment QA as its radius, that circle will be orthogonal to the circle Q1, and it will be orthogonal to the circle Q2. That much we proved in the previous lectures. Now, this is captured over here in this line, the circle Q thus constructed. In other words, the circle whose center is the point Q and the radius is the length of the line segment QA is orthogonal to the input circles Q1, 2, and we will also agree that the circle Q intersects the line of centers at the points O1 and the point O2, and we can agree that we name these points or assign their subscripts 1 and 2 in such a way that we pick one point, let's say O1, that is located on the same side with respect to the radical axis as the side on which the center of the circle Q1 is located. O1, Q1, it doesn't matter, minor detail. O2, the point O2 is located on the same side with respect to the radical axis of the input circles on which the center of the circle Q2 is located, just to be nice and neat and convenient. Now, what can we say about the circle Q? Well, the circle Q is actually orthogonal to 4 objects at once. Our circle Q is orthogonal to the straight line of centers. It is orthogonal to the radical axis of 2 circles, and it is orthogonal to the input circle Q1 and the circle Q2 at the same time. So now is the opportune moment to pick and define our parameters of inversion. Here I define, if you think about it on your own, you will realize that the circle of inversion that will solve the given problem can be defined in 2 distinct ways. The center of that circle can be placed at the point O1, which we already agreed how to locate and how to assign, and the radius of the circle of inversion will be taken to be equal to the diameter of the circle Q, or the distance between the points O1 and O2. Likewise, we can define the circle of inversion that will solve the problem if it has the center of the point at the point O2, but the radius of that circle is still equal to the diameter of the circle Q orthogonal to both circles Q1 and Q2, and that will be the distance between the point O2 and O1. In that case, what will happen? Well, let us think together. Under the inversion of the parent plane with respect to the circle here, C, thus defined, for example, what will happen? The straight line L will be taken into itself because it passes through the center of inversion. I put the small dotted circle around the center of inversion. This is the circle of inversion C, shown partially in dashed line in green. We do not really need it. We understand what's going on. We know the parameters of this inversion. The power of inversion is positive. We will work with the positive power of inversion. So our radius of inversion, which is this distance right here, is taken, square of it is taken with the plus sign. The power of inversion is positive. So what will happen next? Well, our circle Q passes through the center of inversion, and it is tangent to the circle of inversion internally at the point O2 by the corresponding theorem. Under the inversion of the parent plane with respect to the circle C with positive power, one inversion will take this circle Q where? It will take this circle Q into this straight line, to which I referred as Q prime. That straight line will be orthogonal to the straight line of centers L. Why is that? Well, that straight line must be tangent to the circle of inversion at the point of tangency right here, and that means that it must be perpendicular to the corresponding radius, which is housed by this straight line of centers. So that must be the case. as is shown over here with a squarey angle sign, as it is over here as well. Now, what other tactical observation can we make here after that? Well, if our input circle, if our circle Q is orthogonal to both of the input circles Q1 and Q2, again, remember by the corresponding theorem, the magnitude of the angles between cooperating curves under any inversion is preserved. It means that the images of the circles Q1 and Q2 under the corresponding inversion must be also what? They must be orthogonal to the image of the circle Q, or they must be orthogonal to the straight line Q prime. And how can this ever be? Well, this can only be if the centers of the image circles Q prime 1 and Q prime 2 are located somewhere on that straight line Q prime. That's on the one hand. On the other hand, as we observed very early in our reasoning, precisely because the input circles Q1 and Q2 are orthogonal to the straight line L, then under the corresponding inversion of the parent plane with respect to the corresponding circle with positive power ones, the images of all these objects must be orthogonal as well. The straight line L is taken into itself, and the circles Q1 and Q2 must be taken into genuine circles which are orthogonal to the straight line L, which means the centers of the image circles must also be somewhere on the straight line L. Now, how do we know that our input circles under the chosen inversion are taken into genuine circles and not into straight lines? Well, due to the machinery of how these things work, mutual juxtaposition, radical access, the way we constructed the circle Q, the point O1 will be positioned in such a way that neither the circle Q1 nor the circle Q2 will pass through it. And by the corresponding theorems that we proved earlier, that means that under the chosen inversion, the circles Q1 and Q2 will be taken into genuine circles. And now we pretty much solved the problem, because now we have the method of intersecting loci at its best. The centers of the image circles Q'1 and Q'2 must be, on the one hand, located somewhere on the straight line L, and on the other hand, the centers of the image circles Q'1 and Q'2 must also be located somewhere on the straight line Q prime. And how can these two requirements be possibly reconciled? Well, there is only one to reconcile these two requirements. That means that the images of the circles Q1 and Q2, which again I do not show in order to avoid the clutter, they must merge precisely into the point O2, this point right here. And this is what I captured over here. If for the center of inversion we pick the point O1, then the images of the input circles Q1 and Q2 will be concentric with respect to the point O2. In other words, the point O2 will play the role of the center of both image circles Q1 and Q2 under the inversion with respect to the circle C. If we were to make the point O2 the center of inversion, then which point will play the role of the centers of the concentric images of the circles Q1 and Q2? The point O1, of course, evidently. And this is it. We have solved the problem completely by performing this analysis. And in order to show you, again, because on the board I did not portray the circles, for example, in this case, the circle Q2 will actually be taken into a manageable circle that is centered at the point O2, but the larger circle Q1 usually becomes so large it doesn't fit, and doesn't fit on the screen. I recommend that you carry out this construction, you implement this idea using your favorite graphing software, whatever you use. I use free software called GeoGebra, but once you do that, you will see that the radius of the image of the circle Q1 becomes just way too large. It will not likely fit inside your screen or the viewport provided by your graphing software. So that is why here I did not even pretend it, but I have put together an animation using the free software called GeoGebra for you. And in that animation, I followed precisely that algorithm. You will see the input circles shown in dashed lines, and the centers of the circle will move ever so slightly because the radii of the image circles are very sensitive to the mutual juxtaposition of the circles. Even the small deviations of the centers can produce very large effect on the radius of the image circle. So you will see the input circles move ever so slightly towards each other a little bit, but pay attention to the circles that are the images of the circles in the circle C that we defined over here. I portrayed these image circles in two different colors in very heavy lines, and you will see even though the input circles move a little with respect to each other, their images remain exactly concentric at all times. This seminar is based on the corresponding chapter from my free book, Inversive Geometry for All. The link to that PDF file in which this chapter is available free of charge is in the comment section to this episode. If you missed anything or if you have any questions, try to read through the printed material first. But if you're still confused about something or something is not clear, then by all means do ask. Now that we understood the analysis of this problem, we can put together an algorithm that solves the problem number 17. To that end, if the two input circles are located strictly one outside of the other, then the following algorithm will produce an inversion of the parent plane with respect to the circle that we will define, that will take these two distinct circles that are not in contact and that are located one outside of the other into two concentric circles. Step number one, construct the straight line of centers Q1, Q2, where the points Q1 and Q2 are the centers of the input circles Q1, Q1, and Q2, Q2. That can be done with Euclidean tools alone. Step number two, construct the one external tangent T1, T2 to the input circles Q1 and Q2. If you do not know how to do that, on this channel in Season 2, Episode 6, we explain how to construct both internal and external tangents. There are several ways to do it. Which one you pick, it doesn't really matter. Fundamentally, this task can be done with Euclidean tools alone. Step number 3, once the points of tangency T1 with the circle Q1 and T2 with the circle Q2 identified, we bisect the line segment T1, T2 in order to obtain the point M such that the distance from the point M to the first tangency point T1 and from the same point M to the second tangency point T2 is the same. Bisect T1, T2 to obtain the point M such that this relation over here holds. That's step number 3. Step number 4, construct a straight line A that is orthogonal to the straight line of centers L precisely through the point or at the point M that we obtained over here. That straight line shown in red on the right side of your screen. We know the name of that straight line. This is the radical axis of the input circles. That straight line L will intersect, straight line A will intersect the line of centers L at a unique point, uppercase Q. This point is shown over here. Step number 5, construct a tangent that is tangent QA that comes in contact with the circle Q1 through the point Q. It should be evident that this task is done through the point Q because the letter Q over here, but I will designate it here through the point Q. In other words, in the step number 5, through the point Q, construct a tangent to any circle, let's say circle Q1, at the point A. QA is tangent to the circle Q1, evidently through the point Q. Now, in the step number 6, we now have all the parameters of the circle Q that we need. In other words, as a step number 6, construct the circle Q that has the point Q, uppercase Q, as its center. We'll locate this point Q in the step number 4, and it has the distance from the point Q to the point A, the tangency to the circle Q1 as its radius, center, radius, center. Now that circle Q will intersect the straight line of centers L over 2 distinct points, the point O1 and the point O2. O1, O2, and essentially the game is over in the second step. If we want to branch it out in a separate step, we have a choice of constructing 2 circles. We either construct the circle C1 that has the point O1 as its center, or we can construct the circle C2 that has the point O2 as its center. Point O2 is the center. Which one we pick, it doesn't really matter. Either way, the radius of inversion in this case is important. We pick it specifically to be the diameter of the circle Q, or the distance between the points O1 and O2. The distance between the points O1 and O2. In the first case, we put the needle of the compass in the point O1, open up the compass to the distance O2, snap a circle. In the second case, we put the needle of the compass into the point O2, open that compass to cover the distance O2, O1, and snap a circle. And then the inversion of the parent plane with respect to either circle thus defined with positive power. Remember, we have a choice for positive or negative power. Here we choose the power to be positive, and under these parameters, the input circles Q1 and Q2 will be taken into the concentric circles, when in the first case we already know the opposite point will be the center of both image circles, the point O2, and in the first case it will be the point O1. Now this is it for the problem number 17, and in the next seminar, in the seminar number 8, we will solve a very interesting and quite famous problem that is known as the chain of Pappus.